Intel is planning an improvement to their future processors, which may prevent some kinds of attacks.
Hey, Matt, I guess I've been around for a while. It's good to see you, by the way.
Good to see you.
I've been around for a while, and, over the years, they've been introducing like segmentation functions, memory randomization functions, direct memory access controls, trusted computing modules, and, I think they're continuing to make some headway in improving the capabilities for processing, that is processing hardware to help protect against, malicious activities. But it looks like you've found an article here that takes it a step further. Can you tell us a bit about it?
Sure thing. So this is an announcement from Intel. They've got this new technology they're calling Control Flow Enforcement Technology, or CET. I guess you pronounce it CET or CET, I'm not sure. But the whole point of this technology is to prevent certain types of manipulation of the stack. In particular, most people might know return-oriented programming. So this was something they published about in 2016. So they've had the idea for a while, but they've just announced that the new Tiger Lake processors that are coming out in the near future will be the first microarchitecture to have this. So the big question is, what is this all about? And to explain that, I kind of have to take a few steps back. So one of the classic attacks on processors is buffer overflow. So basically in a buffer overflow, what you're trying to do is gain control of the current instruction, and you do that by manipulating things on the stack. And you kind of need to know the right memory location to jump to in order for your attack to work and point to the code you've also loaded in. So over the years, processor designers have come up with new ways of preventing this, and operating system implementers the same. There are things that you might have heard of called address space layout randomization, and then executable space protection, which you might know from Windows as DEP, or data execution prevention. And these are the sorts of things that make that specific attack much harder, place things in places in memory that you can't really predict, and then make certain things non-executable. So even if you put something there, it'll never be treated as executable code. So ROP came in a few years back, and ROP, return-oriented programming, is basically a way of saying, well, if I can't write my own code, what I'll do is I'll grab bits and pieces from code that I know is in a known place on the system, like libc. Return-oriented programming, I think the first time I've ever heard of it was when it was called return to libc, where as long as you know what kind of code is somewhere in those libraries, like those base libraries in C, you can kind of cut and paste your own and then hop through it to get done what you want to get done, which was pretty cool at the time, and still kind of, if you're doing that sort of work today, if you're writing exploits, you kind of have to know ROP if you're running it on a modern operating system.
Mm-hmm.
But what Intel has done, they've got this CET, and the whole idea is, instead of using a regular stack, they've got what's called a control stack. So even if you're messing with the regular data stack on a system, when the code returns, if there's any sort of change, if there's difference between the control stack and the data stack, it halts execution and says somebody's messing with my code, they're trying to exploit it, shut the process down, which is good, which means that this very fundamental thing that you need to know in order to exploit things by stack smashing, and there are variations on ROP as well, but it seems to be a pretty good way of making this even more difficult.
This is happening at runtime, so
Yep.
That helps, right? Because no matter how it gets inserted, from what source, how long it's been there, when it tries to run, the chip is going to see that and stop it.
Right. So it does require that the operating system is also aware and supports this function. They kind of have to work together. And right now, I think Windows 10 version 2004 supports it, and I don't know of any others that do. But it's probably a chicken and an egg sort of thing, where people aren't going to support it until the hardware is there, and the hardware is not going to have. See, everyone has to kind of work together to get it to work. But when it does, it sounds like it's pretty promising. I mean, there are some people who have already come out with they're postulating possible ways to get around it, but still, it seems like raising the bar is a good way to do it. Now, Intel has been doing things to their processors for a while to add extra security. One of the interesting things that this is a specific way of preventing malicious behavior instead of like monitoring it or providing an environment for working around it. Like management engine sort of lets you have introspection and look into what's going on in the system. And then SGX is sort of like, I think it was an enclave. They're both different kinds of things that Intel's put in, um, which are all processor security in one way or the other. But this seems to be like a fundamental change in the way that stacks are handled, which is kind of cool. So I'd love to see how this plays out, and I think there's probably going to be a lot of work done in this area in the next couple years as this rolls out, because once this is out there, people are going to start hacking on it. They're going to try and find ways around
There are a few things that I think are really interesting observations here. I think I'll start with the sort of the first, which is, as hardware has become more advanced, I think we're getting to the point where having faster processors, I mean, is obviously desirable when you're doing really high compute situations, but to really it's gotten to the point where we have enough hardware capability that adding more features to support security functions is actually more practical than it had been in the past. And, clearly it's a higher priority than it has been in the past as well. So it's interesting to see that more hardware is being brought into the solution to help make sure that things are processing the way they're supposed to be. And I think of two analogies that are perhaps a little bit close to this. Not entirely, but a little bit close. And unfortunately, they have to do with my long history in security stuff. One, I'll go back to Space Shuttle. And I don't remember all the details around this, but I was reading an article about how the Space Shuttle actually had 5 navigation computers. I think I got the number correct here. And that was to facilitate redundancy more so than anything else, but they actually had more than one navigation software stack that was used in parallel with, and they were actually developed independently. So there was one organization that created the navigation calculations and a separate organization that created a separate set of navigation software so that they run in parallel to make sure that they agreed with each other in terms of how to do the navigation accurately. And then on top of that, they had 5 computers running these so that I think actually 3 of one version was running on three computers, and then you'd have 2 others so that you could actually have any 2 computers fail and still have a legitimate voting algorithm to choose the best navigation path for the space shuttle. So I think that was kind of interesting. And it sounds a little ridiculous, like why so many? But when you're traveling in space, one of the things they were concerned about is when you're using integrated circuits in space, you have the threat of radiation actually penetrating the integrated circuit, actually changing bits in your calculations. And so they were concerned about that and wanted to make sure that wasn't going to be a problem. So having 5 computers perhaps wasn't all that ridiculous. And of course, when they designed Space Shuttle, that was a big deal, making sure that it was really, really reliable. A sort of a similar thing that I'd worked on actually many years ago had to do with basically running cryptographic algorithms. And, when we started out developing cryptographic algorithms, they were all done in hardware exclusively. We did all kinds of analysis to make sure that they wouldn't fail in bad ways. And so as we transitioned into starting to do really high assurance cryptographic algorithms, we were trying to figure out a way you could do it in software and still be able to continue with that assurance. And so what we did is we actually had sort of a parallel process that was running alongside to make sure that there were no undesired changes in the processing steps that were performed. And I won't go into the little secrets that we had at the time for doing that, but it's very similar to this kind of thing, that is to actually have something that's running alongside to check and make sure things aren't going in a way that you didn't expect or the way they shouldn't be. So it's nice to see, in my opinion, really nice to see that more of the engineering is going into making it more secure as opposed to just simply making it bigger or faster.
That's good points. What do you think, Mike?
Yeah, I like the observation that we're going to use hardware to protect. I've been in a lot of conversations where you have resources that are pretty much already tapped out, and you're trying to add something to it to protect it. So it'll be interesting over time to see if we go from the 1% up to maybe getting a decent share of 10 to 20% of the resources that are actually allocated intentionally to protection. So I think it's a great observation. And I had heard a similar concept to this. It wasn't hardware-based, it was software-based. There was kind of an add-on solution where you just had that copy on the side and you were doing these periodic checks. But obviously if it's happening while the code is running, beautiful. And if it's done with hardware, it's going to be fast. So sounds great. Concept at least sounds great.
Well,
of course, buffer overflow attacks have been a menace for years and years and years and years. And to be able to get, further ahead in protecting against a buffer overflow attack is really powerful. I just hope it doesn't, legitimize creating poor code quality.
That's a good point. I would argue that there's enough problems of getting software to run properly, enough other vulnerabilities you could introduce, that I'd really appreciate it if some of the really fundamental ones could be sort of swept under the rug a little bit. That way, at least in general, even if someone still does manage to find a bug, at least the ones that you can fix automatically are handled. So,
yeah, absolutely. Well, I could play counterpoint on my argument there. Quite frankly, a lot of code checks have to be put into place, boundary checks and things to prevent buffer overruns. And quite frankly, if you actually could depend on the hardware to do that, you could save actually a lot of coding, a lot of testing activities to make sure that the software is secure. So, perhaps there's somewhat of a transition, and it's going to be a long transition, I presume, because this is just one technology. There are certainly other, chip manufacturers that provide processing units that would need to catch up or somehow replicate similar kinds of checks. But this would provide, clearly from their point of view, Intel's point of view, this will be a competitive advantage. That is, you want to run things on their processors if you can do coding more efficiently and more effectively, but still securely. So.
Hey, Matt, one more question. When you detect a condition where the code doesn't look right, you just get an abnormal ending, right? It just stops processing?
I think the process just quits. Yeah, I mean, that's probably the best case scenario. I mean, rather than crashing, right, which is what might normally happen unless someone's properly crafted the attack. But yeah, I think that's probably the best case scenario. I mean, it's probably going to be up to the operating systems to decide what to do next. Do you notify the user? Do you not notify the user? But at least whatever problem you were having halts right there. So
yeah, being able to recognize the exception gives you the opportunity to treat the exception in an appropriate way. So it could be, restart the process. It could be you just kind of back up and do something a little differently. But there are lots of options around that. I think, Matt, to what you were alluding to. Mm-hmm. The first step is making sure you recognize that something is awry.
And that's an interesting thing too. I mean, that might be an API you might provide to antivirus or whatever security platform you've already got running to say, hey, this is the software responsible for securing the system. We just found something, and it's up to you guys to do. Do you want to notify the user? Do you want to trace back the execution? Do you want to notify whatever central management system you've got for your antivirus in a corporate environment to say someone tried to exploit this box? I mean, the options are pretty open, but kind of exciting.